Nitrous oxide, commonly known as laughing gas, nitrous, or nose, is a chemical compound, an oxide of nitrogen with the formula N2O. At room temperature, it is a colorless non-flammable gas, and has a slightly sweet scent and taste. At elevated temperatures, nitrous oxide is a powerful oxidizer similar to molecular oxygen. Nitrous oxide has significant medical uses, especially in surgery and dentistry, for its anesthetic and pain-reducing effects. Its colloquial name, laughing gas, coined by Humphrey Davy, is due to the euphoric effects upon inhaling it, a property that has led to its recreational use as a dissociative anesthetic. It is on the World Health Organization's list of essential medicines. It is also used as an oxidizer in rocket propellants, and in motor racing to increase the power output of engines. Nitrous oxide's atmospheric concentration reached 333 parts per billion ppb in 2020, increasing at a rate of about 1 ppb annually. It is a major scavenger of stratospheric ozone, with an impact comparable to that of CFCs. Global accounting of N2O sources and sinks over the decade ending 2016 indicates that about 40% of the average 17 TGN per year, teragrams of nitrogen per year, of emissions originated from human activity, and shows that emissions growth chiefly came from expanding agriculture and industry sources within emerging economies. Being the third most important long-lived greenhouse gas, nitrous oxide also substantially contributes to global warming. Nitrous oxide may be used as an oxidizer in a rocket motor. It has advantages over other oxidizers in that it is much less toxic, and because of its stability at room temperature, it is also easier to store and relatively safe to carry on a flight. As a secondary benefit, it may be decomposed readily to form breathing air. Its high density and low storage pressure, when maintained at low temperature, enable it to be highly competitive with stored high-pressure gas systems. In a 1914 patent, American rocket pioneer Robert Goddard suggested nitrous oxide and gasoline as possible propellants for a liquid-fueled rocket. Nitrous oxide has been the oxidizer of choice in several hybrid rocket designs, using solid fuel with a liquid or gaseous oxidizer. The combination of nitrous oxide with hydroxyl-terminated polybutadiene fuel has been used by SpaceShipOne and others. It also is notably used in amateur and high-power rocketry with various plastics as the fuel. Nitrous oxide also may be used in a monopropellant rocket. In the presence of a heated catalyst, N2O will decompose exothermically into nitrogen and oxygen, at a temperature of approximately 1070 degrees Fahrenheit, 577 degrees Celsius. Because of the large heat release, the catalytic action rapidly becomes secondary, as thermal autodecomposition becomes dominant. In a vacuum thruster, this may provide a monopropellant-specific impulse (ISP) of as much as 180 s. While noticeably less than the ISP available from hydrazine thrusters, monopropellant or bipropellant with dinitrogen tetroxide, the decreased toxicity makes nitrous oxide an option worth investigating. Nitrous oxide is said to deflagrate at approximately 600 degrees Celsius, 1112 degrees Fahrenheit, at a pressure of 309 psi, 21 atmospheres. At 600 psi, for example, the required ignition energy is only 6 joules, whereas N2O at 130 psi at 2500 joule ignition energy input is insufficient. In vehicle racing, nitrous oxide, often referred to as just nitrous, allows the engine to burn more fuel by providing more oxygen during combustion. The increase in oxygen allows for an increase in the injection of fuel, allowing the engine to produce more engine power. The gas is not flammable at a low pressure temperature, but it delivers more oxygen than atmospheric air by breaking down at elevated temperatures, about 570 degrees Fahrenheit, approximately 300 C. Therefore, it often is mixed with another fuel that is easier to deflagrate. Nitrous oxide is a strong oxidizing agent, roughly equivalent to hydrogen peroxide, and much stronger than oxygen gas. Nitrous oxide is stored as a compressed liquid. The evaporation and expansion of liquid nitrous oxide in the intake manifold causes a large drop in intake charge temperature, resulting in a denser charge, further allowing more air-fuel mixture to enter the cylinder. Sometimes nitrous oxide is injected into, or prior to, the intake manifold, whereas other systems directly inject, right before the cylinder, direct port injection, to increase power. The technique was used during World War II by Luftwaffe aircraft with the GM-1 system to boost the power output of aircraft engines. Originally meant to provide the Luftwaffe standard aircraft with superior high-altitude performance, technological considerations limited its use to extremely high altitudes. Accordingly, it was only used by specialized planes such as high-altitude reconnaissance aircraft, high-speed bombers and high-altitude interceptor aircraft. It sometimes could be found on Luftwaffe aircraft also fitted with another engine boost system, MW-50, a form of water injection for aviation engines that used methanol for its boost capabilities. One of the major problems of using nitrous oxide in a reciprocating engine is that it can produce enough power to damage or destroy the engine. Very large power increases are possible, and if the mechanical structure of the engine is not properly reinforced, the engine may be severely damaged, or destroyed, during this kind of operation. It is very important with nitrous oxide augmentation of petrol engines to maintain proper operating temperatures and fuel levels to prevent pre-ignition, or detonation, sometimes referred to as knock. Most problems that are associated with nitrous oxide do not come from mechanical failure due to the power increases. Since nitrous oxide allows a much denser charge into the cylinder, it dramatically increases cylinder pressures. The increased pressure and temperature can cause problems such as melting the piston or valves. It also may crack or warp the piston or head and cause pre-ignition due to uneven heating. Automotive-grade liquid nitrous oxide differs slightly from medical-grade nitrous oxide. A small amount of sulfur dioxide, SO2, is added to prevent substance abuse. Multiple washes through a base, such as sodium hydroxide, can remove this, decreasing the corrosive properties observed when SO2 is further oxidized during combustion into sulfuric acid, making emissions cleaner. The gas is approved for use as a food additive, E number E942, specifically as an aerosol spray propellant. Its most common uses in this context are in aerosol whipped cream canisters and cooking sprays. The gas is extremely soluble in fatty compounds. In aerosol whipped cream, it is dissolved in the fatty cream until it leaves the can, when it becomes gaseous and thus creates foam. Used in this way, it produces whipped cream which is 4 times the volume of the liquid, whereas whipping air into cream only produces twice the volume. If air were used as a propellant, oxygen would accelerate rancidification of the butterfat, but nitrous oxide inhibits such degradation. Carbon dioxide cannot be used for whipped cream because it is acidic in water, which would curdle the cream and give it a seltzer-like, sparkling, sensation. The whipped cream produced with nitrous oxide is unstable, however, and will return to a more liquid state within half an hour to 1 hour. Thus, the method is not suitable for decorating food that will not be served immediately. During December 2016, some manufacturers reported a shortage of aerosol whipped creams in the United States due to an explosion at the Air Liquide Nitrous Oxide facility in Florida in late August. With a major facility offline, the disruption caused a shortage resulting in the company diverting the supply of nitrous oxide to medical clients rather than to food manufacturing. The shortage came during the Christmas and holiday season when canned whipped cream use is normally at its highest. Similarly, cooking spray, which is made from various types of oils combined with lecithin, an emulsifier, may use nitrous oxide as a propellant. Other propellants used in cooking spray include food-grade alcohol and propane. Nitrous oxide has been used in dentistry and surgery, as an anesthetic and analgesic, since 1844. In the early days, the gas was administered through simple inhalers consisting of a breathing bag made of rubber cloth. Today, the gas is administered in hospitals by means of an automated relative analgesia machine, with an anesthetic vaporizer and a medical ventilator, that delivers a precisely dosed and breath-actuated flow of nitrous oxide mixed with oxygen in a 2:1 ratio. Nitrous oxide is a weak general anesthetic, and so is generally not used alone in general anesthesia, but used as a carrier gas mixed with oxygen for more powerful general anesthetic drugs such as sevoflurane or desflurane. It has a minimum alveolar concentration of 105% and a blood-gas partition coefficient of 0.46. The use of nitrous oxide in anesthesia, however, can increase the risk of postoperative nausea and vomiting. Dentists use a simpler machine which only delivers an N2O-O2 mixture for the patient to inhale while conscious. The patient is kept conscious throughout the procedure, and retains adequate mental faculties to respond to questions and instructions from the dentist. Inhalation of nitrous oxide is used frequently to relieve pain associated with childbirth, trauma, oral surgery, and acute coronary syndrome, includes heart attacks. Its use during labor has been shown to be a safe and effective aid for birthing women. Its use for acute coronary syndrome is of unknown benefit. In Britain and Canada, Entonox and Nitronox are used commonly by ambulance crews, including unregistered practitioners, as rapid and highly effective analgesic gas. 50% nitrous oxide can be considered for use by trained non-professional first aid responders in pre-hospital settings, given the relative ease and safety of administering 50% nitrous oxide as an analgesic. The rapid reversibility of its effect would also prevent it from precluding diagnosis. Recreational inhalation of nitrous oxide, with the purpose of causing euphoria and/or slight hallucinations, began as a phenomenon for the British upper class in 1799, known as laughing gas parties. Starting in the 19th century, widespread availability of the gas for medical and culinary purposes allowed the recreational use to expand greatly throughout the world. In the United Kingdom, as of 2014, nitrous oxide was estimated to be used by almost 500,000 young people at night spots, festivals, and parties. The legality of that use varies greatly from country to country, and even from city to city in some countries. Widespread recreational use of the drug throughout the UK was featured in the 2017 Vice documentary Inside the Laughing Gas Black Market, in which journalist Matt Shea met with dealers of the drug who stole it from hospitals. Although with nitrous oxide canisters being readily available online, the incidents of hospital theft are expected to be extremely rare. A significant issue cited in London's press is the effect of nitrous oxide canister littering, which is highly visible and causes significant complaint from communities. The major safety hazards of nitrous oxide come from the fact that it is a compressed liquefied gas, an asphyxiation risk, and a dissociative anesthetic. While relatively non-toxic, nitrous oxide has a number of recognized ill effects on human health, whether through breathing it in or by contact of the liquid with skin or eyes. Nitrous oxide is a significant occupational hazard for surgeons, dentists, and nurses. Because nitrous oxide is minimally metabolized in humans with a rate of 0.004%, it retains its potency when exhaled into the room by the patient, and can pose an intoxicating and prolonged exposure hazard to the clinic staff if the room is poorly ventilated. Where nitrous oxide is administered, a continuous flow fresh air ventilation system or N2O scavenger system is used to prevent a waste gas buildup. The National Institute for Occupational Safety and Health recommends that workers' exposure to nitrous oxide should be controlled during the administration of anesthetic gas in medical, dental, and veterinary operators. It set a recommended exposure limit, REL, of 25 ppm, 46 mg per cubic meter, to escaped anesthetic. Occupational exposure to ambient nitrous oxide has been associated with DNA damage, due to interruptions in DNA synthesis. This correlation is dose-dependent and does not appear to extend to casual recreational use. However, further research is needed to confirm the duration and quantity of exposure needed to cause damage. Long-term exposure to nitrous oxide may cause vitamin B12 deficiency. It inactivates the cobalamin form of vitamin B12 by oxidation. Symptoms of vitamin B12 deficiency, including sensory neuropathy, myelopathy, and encephalopathy, may occur within days or weeks of exposure to nitrous oxide anesthesia in people with subclinical vitamin B12 deficiency. Symptoms are treated with high doses of vitamin B12, but recovery can be slow and incomplete. People with normal vitamin B12 levels have stores to make the effects of nitrous oxide insignificant, unless exposure is repeated and prolonged nitrous oxide abuse. Vitamin B12 levels should be checked in people with risk factors for vitamin B12 deficiency prior to using nitrous oxide anesthesia. The gas was first synthesized in 1772 by English natural philosopher and chemist Joseph Priestley, who called it dephlogisticated nitrous air, see phlogiston theory, or inflammable nitrous air. Priestley published his discovery in the book Experiments and Observations on Different Kinds of Air, 1775, where he described how to produce the preparation of nitrous air diminished by heating iron filings dampened with nitric acid. The first important use of nitrous oxide was made possible by Thomas Beddoes and James Watt, who worked together to publish the book Considerations on the Medical Use and on the Production of Factitious Airs, 1794. This book was important for two reasons. First, James Watt had invented a novel machine to produce factitious airs, including nitrous oxide, and a novel breathing apparatus to inhale the gas. Second, The book also presented the new medical theories by Thomas Beddoes, that tuberculosis and other lung diseases could be treated by inhalation of factitious airs. The machine to produce factitious airs had three parts: a furnace to burn the needed material, a vessel with water where the produced gas passed through in a spiral pipe, for impurities to be washed off, and finally the gas cylinder with a gasometer where the gas produced air could be tapped into portable air bags made of airtight oily silk. The breathing apparatus consisted of one of the portable air bags connected with a tube to a mouthpiece. With this new equipment being engineered and produced by 1794, the way was paved for clinical trials, which began in 1798 when Thomas Beddoes established the Pneumatic Institution for Relieving Diseases by Medical Airs, in Hotwells, Bristol. In the basement of the building, a large-scale machine was producing the gases under the supervision of a young Humphrey Davy, who was encouraged to experiment with new gases for patients to inhale. The first important work of Davy was examination of the nitrous oxide, and the publication of his results in the book, Researches, Chemical and Philosophical, 1800. In that publication, Davy notes the analgesic effect of nitrous oxide at page 465 and its potential to be used for surgical operations at page 556. Davy coined the name, laughing gas, for nitrous oxide. Despite Davy's discovery that inhalation of nitrous oxide could relieve a conscious person from pain, another 44 years elapsed before doctors attempted to use it for anesthesia. The use of nitrous oxide as a recreational drug at laughing gas parties, primarily arranged for the British upper class, became an immediate success beginning in 1799. While the effects of the gas generally make the user appear stuporous, dreamy and sedated, some people also get the giggles, in a state of euphoria, and frequently erupt in laughter. One of the earliest commercial producers in the U.S. was George Poe, cousin of the poet Edgar Allan Poe, who also was the first to liquefy the gas. The first time nitrous oxide was used as an anesthetic drug in the treatment of a patient was when dentist Horace Wells, with assistance by Gardner Quincy Colton and John Mankey Riggs, demonstrated insensitivity to pain from a dental extraction on the 11th of December 1844. In the following weeks, Wells treated the first 12 to 15 patients with nitrous oxide in Hartford, Connecticut, and, according to his own record, only failed in 2 cases. In spite of these convincing results having been reported by Wells to the Medical Society in Boston in December 1844, this new method was not immediately adopted by other dentists. The reason for this was most likely that Wells, in January 1845 at his first public demonstration to the medical faculty in Boston, had been partly unsuccessful, leaving his colleagues doubtful regarding its efficacy and safety. The method did not come into general use until 1863, when Gardner Quincy Colton successfully started to use it in all his Colton Dental Association clinics that he had just established in New Haven and New York City. Over the following 3 years, Colton and his associates successfully administered nitrous oxide to more than 25,000 patients. Today, nitrous oxide is used in dentistry as an anxiolytic, as an adjunct to local anesthetic. Nitrous oxide was not found to be a strong enough anesthetic for use in major surgery in hospital settings, however. Instead, diethyl ether, being a stronger and more potent anesthetic, was demonstrated and accepted for use in October 1846, along with chloroform in 1847. When Joseph Thomas Clover invented the gas ether inhaler in 1876, however, it became a common practice at hospitals to initiate all anesthetic treatments with a mild flow of nitrous oxide, and then gradually increase the anesthesia with the stronger ether or chloroform. Clover's gas ether inhaler was designed to supply the patient with nitrous oxide and ether at the same time, with the exact mixture being controlled by the operator of the device. It remained in use by many hospitals until the 1930s. Although hospitals today use a more advanced anesthetic machine, these machines still use the same principle launched with Clover's gas ether inhaler, to initiate the anesthesia with nitrous oxide, before the administration of a more powerful anesthetic.